So good afternoon, everyone. Today I will talk about domain kinetics in critical and off-critical binary mixtures. So here is the plan of my talk. First, I will give you a brief introduction to active matter. So I will skip this part as the audience doesn't need any introduction to active matter. Then I will talk about the phase transition in active binary mixtures. So I will begin with the model which I have studied, and finally I will conclude my talk with a summary. So I will begin with the one-dimensional run and tumble vectorial motion. So here this open circle represents a left moving bacterium, and this closed circle represents a right moving bacterium. Okay, so we define this average occupancy of ith site by rho I plus minus. So plus sign is for right moving particle and minus sign is for left moving particle. Okay, then we define di plus as the jump rate of a right moving particle to jump from site I to I plus 1, and this right moving particle can become a left moving particle by doing some tumble. So that corresponding tumbling rate is alpha I plus. So similarly, we define di minus for left moving particle and alpha I minus for the tumbling rate of a left moving particle. Next, we define pk plus is the probability to finding a right moving bacterium at site k. And then similarly, we have pk minus is the probability to find a left moving bacteria at site k. Okay. So next we write the master equation. So the master equation for pk plus is look like this. So the first term is the gain term. So due to jump of a bacterium, right moving bacterium from site k plus 1, k minus 1 to k, and this is the loss term due to jump of a right moving bacterium from site k to k plus 1, and this is the gain term due to tumbling from a left moving particle, and this is the loss of probability due to tumbling of a right moving particle. So similarly, we have the master equation for pk minus 1. Next, we write the continuum limit, and this is what it look like. So in 2D, so this is the master equation we have. Okay, so we have introduced a dynamical variable sigma L here. So sigma L is 1 when we are in the jump state. Okay, and sigma L is 0 when we are in the tumbling state. Okay, so next we coarse gain this equation. So to coarse gain it, we define a variable QRT, which is the probability of finding a particle irrespective of its direction of motion, and we also sum over this sigma. Okay, so after considering the large system size and neglecting the fast moving variable, this is the evolution equation for Q, and D is the diffusivity, which look like this, and F is the effective force. This is what it look like. So the corresponding Ito-Langevin dynamics look like this. Next, we consider a n-body problem. Okay, n-body non-interacting problem. So the corresponding evolution equation for the density field look like this. So here we use the Ito calculus. Okay. So now the diffusivity depends on the density, and the form of the diffusivity look like this, and the effective force look like this. Okay, so the evolution equation for the density field look like this, and D effective is the effective diffusivity which has this form. Okay. And then it has been shown in this paper that this model can be generalized to n-component system, and the evolution equation for the ith component look like this. So here this term is the phenomenological term which we have put to incorporate the interface between the different components of the mixture. So next we rescale the time, and this is what the evolution equation become. Here we also neglect the thermal noise term. Okay. So in this paper, it has been shown that for one component system with Coulomb sensing interaction, one can map this equation to a equilibrium free energy with some ideal gas-like time term and a local interaction term. For n-component system, so this is what it look like, and the corresponding velocity will become this. From this, we derive the condition of instability, and the condition of instability look like this. Okay. So when we set lambda greater than 0, so the particles become mutually activating. So in this context, we get phase separation. When we set lambda less than 0, we get mutually inhibiting system. So particle in this case coexist. Yeah, so we consider a binary mixture. So we take ax, b1 minus x, and we have the evolution equation, which is look like this, and the velocity are calculated from the previous expression, something exponential, some rho vi. Okay, so we numerically solve this equation. We set the parameter value k equal to 1, and we discretize this equation using Euler discretization technique. So we set delta x to be 0.5 and dt equal to 0.001. Okay, for critical binary mixture, our x is 0.5. So basically 50% A, 50% B, and the average density of A and B is we set to be 12.5. So that gives lambda something like, we use something like 0.085 that satisfies the instability condition. And the initial condition for this rho A and rho B is like average value 12.5 plus minus 0.01. So similarly, we use for a critical mixture, we set x equal to 0.3, and these are the number we have used. And then we define order parameter like this. So if a site is occupied by a site, so A particle, then psi is positive. If it is occupied by B particles, then the psi is -1. So this is the So this is the evolution snapshot for 50-50 binary mixture. So we have interconnected domain structure. At early time, we have small, the domain sizes are small. As time advances, this domain size increases with time. Here, the A-rich domains are, A-rich regions are marked in black, and the B-rich regions are kept unmarked. Okay. So the question we ask in this context is like how this domain size grow in time, and what is the morphology of this domain growth. So to do that, we calculate the equal time correlation function. So it is defined like this, and also we calculate the structure factor, which is the Fourier transform of the equal time correlation function. So here is the plot for equal time correlation function, and here we normalize the distance or scale the distance by the average domain size L. And what is L, I will tell you. Okay, so clearly we see a dynamical scaling. Okay, so correlation function at different times fall onto each other. Okay, so that implies that the domain morphology is self-similar in time. And also we calculate the structure factor. So the tail of the structure factor decays as k to the power -3. So that implies that the interface between A-rich and B-rich domain is sharp. Okay. So just one thing. So next we calculate the length scale, which is defined as the distance at which correlation function falls from its maximum value 1 at r equal to 0. Okay, so this is what we found, that LT goes as t to the power 1/3. This is similar to diffusive growth. So although the effective diffusion coefficient depends on density. Okay, so next, just 30 seconds. So next we introduce the critical mixture. So in this case, we get droplet-like morphology. We see correlation, scaling of correlation function quite well, although there is some discrepancy. The tail of the structure factor follows the forward tail, but the average domain size grows as t to the power 1/3 instead of 1/4 instead of 1/3. Okay, so these are our preliminary data. I mean, so we have to make sure that this is correct. Okay, so probably this is coming from the effective diffusivity that depends on the density, and the density is not same for A and B for the critical case. Okay, so this is what we think. So thank you for your attention. Yes.
It appears that the effect of surface tension is very strong, right? So is there any passive interaction of some sort, or it's appearing from the dynamical interactions?
So it is coming from dynamical interaction. So the surface term we put by hand, that del to the power 4 term.
Okay, so that's equivalent to some sort of passive interaction.
Yes, yes, yes. So I mean, otherwise we cannot incorporate.
So the phase separation that you are seeing here in the final results is for two different kinds of bacteria, because you started with the run and thermodynamics, then you extended it for 2 dimension, and then you went to the continuum limit, right? Did I get it correct? Okay, thank you.
And the best thing about this model is like you can generalize this to 3-component mixture, 4-component mixture, because they are separate.
Can I ask a question?
Yes.
So how should I interpret this lambda greater than whatever 1 by rho A rho B
yes,
in terms of the original dynamics? I mean, you have done a lot of
Yes. So yeah. So
approximations,
yes,
but in
yes.
terms of the original dynamics, how
So
do you?
yes. So lambda appears here. Okay. So the interaction like
Yeah, so this
rho A, rho
condition
B.
lambda square greater than 1 by rho A rho B.
Yes. So that comes from, so if you define a Hessian from this free energy, so like the partial
No, but
derivative.
if I just forget all that and I look at your original model,
Uh-huh.
you had these 4 rates with plus and minuses, right? For right, left hopping and this
And then
conversion.
2D, it is like a continuous vector. So for 2D, it is continuous vector I made.
No, but I was asking, how should I interpret this in terms of the parameters, the 4 parameters that you have? Can you say clearly which parameter?
So the parameters, so here, so you have a parameter beta. So that is the jumping parameter. So alpha and beta, and we set alpha equal to beta in this case. So they are there.
Okay.
Yeah. So,
okay, I can ask you later.
yes, yes.
Okay, let us thank the speaker.